Yeah.
Good afternoon, dear authors and invited guests. It is my great pleasure to welcome you to the 6th International Congress on Information and Communication Technology through Zoom on behalf of ICICT 2021 and Global Knowledge Research Foundation. As every one of us is passing through unseen circumstances due to COVID-19, we wish everyone and their families a safe time, and we all will together pass this soon. Further, with immense happiness, I would like to share that we have received an overwhelming response this year from across 90 countries, where 1,150 papers were received and 350 papers were accepted, contributing to the success of this conference, and the papers were published in 4 volumes this year. We are thankful to all our guests present on this platform to join us digitally for the conference in these unpredictable times and make this conference more fruitful in terms of technical knowledge, and hope you will enjoy the 2 days of knowledgeful and interactive sessions. I would like to welcome you to the technical session number 2 and further introduce you all to the chair for this session, Alina Mero. Okay, now. Alina Mero is an associate lecturer at Brunel University. She has obtained her PhD in computer vision from INSA Rouen, France, on the topic of pedestrian detection for intelligent vehicles. She worked for several years in industry as a programmer and data scientist, as well as postdoc at Reading University, working on the topic of gesture recognition, and as a research fellow at Brunel University for an intelligent telerehabilitation project. Her main areas of interest are machine learning, artificial intelligence, and computer vision. Okay, so our next presenter is S.W. Mason, presenting a theory and calculation of zero-point energy and pressure, also resulting in a new value for the Hubble constant. The floor is yours, S.W. Mason. You have 10 minutes. I'll notify you on the 10th minute that you have 2 minutes left. The floor is yours.
I don't believe Mr. Mason is in this presentation, is he?
He is, but he's not yet present.
I think Mr. Mason is right now not here in this presentation. So I think we can move on to the next presentation for the timing. And if he joins later, then we can have it.
Okay, so our next, let me share my screen. Our next presenter is Jun Jet Tai, a fast railway fastener detector, as a paper title. The floor is yours.
Hi, I think there's a typo in my name in that flyer, just a minor detail. There we go. Can everybody see my screen?
Yes, the floor is yours.
Okay. Do you see the presentation slide, or do you see like everything else?
We see the presenter view.
I think
it's 11th slide. You need to start from the first. What we are seeing is the 11th slide.
All right, there we go.
Yeah.
All right. So yeah, my name is Junjet. I am currently doing my PhD at Coventry University. And I'm here to present Fastnet, which is a fast railway fastener detector. So just a brief overview about what I'm presenting. What is Fastnet? So Fastnet is an algorithm for performing very fast object detection. So you can imagine this bubble right here is a set of all object detection tasks. Fastnet performs is an algorithm for performing object detection on a subset of these object detection problems. And in this particular presentation, I'm going to present a pilot case where Fastnet is used for fastener detection, hence the name. Just a quick update of what object detection is. This is object detection. The goal is, given an image, you want to draw bounding boxes around each object. and then you want to associate each bounding box with the object inside the bounding box. So for as an example, in this case, you have things like you have a car, you have a dog, horse, person. This is another example, and this can also be applied to videos, in which case where you need a good computational performance. So how is object detection usually done? How it's usually done is you have an image. You usually pass it through a function approximator. This is usually a neural network of some of the more popular networks are like the RCNN and the YOLO family of architectures. What then happens is the network outputs a bunch of bounding boxes as a set of labels, which indicate, for example, the first 4 values would probably be something like your bounding box regressors, and then after that you have your class scores for whatever's inside the box. You pass it through a suppression mechanism, which is the more popular one is non-maximal suppression, which just looks at given these boxes that are overlapping, which of them are the more important ones, and it suppresses out whichever is not important. And then finally you get out some really nice clean detections. So some downsides of the current implementation and why this as a generic object detection framework, it works well for everything, but for some things it doesn't work very well. Some reasons why is redundant detections don't do anything. Multiple detections of the same object, they don't do anything for performance. You can detect the same object 1,000 times, but in the end, once you suppress it, you're only going to get one output detection. So making an network perform more detections per object doesn't really make sense. Regressing bounding boxes is also rather expensive. At a minimum, you require 4 values to describe a bounding box. You also require possibly anchor boxes, and anchor boxes are just default boxes from which the neural network would warp to fit the objects that it sees in the images. And you may also require multiple bounding boxes per spatial location. So some examples would be multiple anchor boxes so that your neural network would then have more boxes to more suitably represent the distribution of data. And then this is expensive. Why? Because, so take for example, okay, you also require an objectness score or a background class. And this is expensive because, take for example, you want your neural network to perform 3 bounding boxes per spatial location plus 1 class. That's already 13 output values per spatial location, which gets if you're detecting like 100 different object classes, that's fine, because it would just be 13 plus 100. But it would just be 12 plus 100. But if your task is really lightweight, you want to detect 1 or 2 classes, this doesn't really make any sense. So this is where we present Fastnet. Fastnet works on a special class of object detection, as mentioned earlier. This special class includes objects that there are no object overlaps, and they are fairly constant object sizes. You may say this is like a very small subset, but this is actually pretty wide. Some examples are pothole detection for road driving. You also have car counting from satellite imagery, and in our case, we are performing fastener counting on railways. So this is our pilot case. We want to detect fasteners from images generated from a new measurement train. The image size is 512 by 1600. This is fairly large in the object detection realm, and the data set is about 700 training images with 300 testing images. The images look like that. As you can tell, the objects are not particularly very large. You can consider them as small object detection as well. Not all images look like that. Some have very, very bad lighting. Some have very odd geometries that they are not supposed to be fasteners. And some also have bad lighting in addition to like fasteners, and then so the key idea of Fastnet is this. You're presented with an image, and then you want to output a saliency map. So what a saliency map is it's just an output map of outputs, and then each output can go from 0 to 1, which is indicative of what the network thinks should be a fastener or not. And then what you do is you pass this saliency map through a thresholding operation. For every pixel in the map, as long as the pixel is above a certain value theta, you're going to seal it to 1, otherwise you're going to floor it to 0. And finally, to get your individual object detections, you just perform a contour finding algorithm to identify individual instances. Contour finding algorithms are not new by any chance. They've been around since the 1950s. We use an algorithm that's been developed in the 1985. It's very popular in the OpenCV framework. It just walks through the entire image, and every time it sees an output pixel white, it just follows the boundary of it and then classifies it as contour. So in this example, we use this Fastnet architecture. It's a fairly simple architecture, nothing too complicated, because the goal of it is to demonstrate that neural networks can actually perform detection when framed like this. So the network is a fully convolutional network with patch normalization. So there's no fully connected layers at the end. It can be used on images of various sizes depending on the scaling ratio of the network. It's 11 full layers. There's an 8-to-1 input output ratio. So for example, the input is 1600 by 512. The output would then be 200 by 64. It has about 500,000 parameters, slightly under 2 megabytes weight file. This is very, very lightweight for a neural network. We use the sigma at the output to represent the saliency map, and then we also use Lee-Kirelu function everywhere else. We train with MSE loss, and we train against segmentation mask. This is different compared to conventional object detection, where you actually train against the values for the bounding boxes. And then the effective receptive field at the middle of the network is about 1.5 times the size of a fastener. So at any given time, every pixel in the center of the network would correspond to 1.5 times a fastener. So in that sense, this network is kind of very specifically designed for this task. We train using hard negative mining and random crowd augmentation. And in the end, the network performs about 30 predictions per fastener. And this is actually helpful because some examples is like this. So given this input image, this is a 256 by 256 crop. And then the output would then be a roughly 32 by 32 crop. And then each prediction will be about 6 pixels high and 5 pixels wide. But this can vary across different fasteners. And from here, you can already tell that more predictions work towards the network's performance. So if the network is really unclear about it, it may predict only a few pixels here. And from there, you can directly tell that the network is not confident with this prediction at all. So after the training part, the network actually performs with about 110 FPS with all the bells and whistles on a GTX 1080, and about 200 FPS on a Tesla V100. This is actually really, really good performance. Most cameras don't even perform this fast. And we actually achieve 99% precision and 91% recall. Some examples of what the predictions look like. So right here, the red boxes are the ground truth predictions, and the green boxes are what the network actually predicts. You can tell that it actually performs pretty well. And in some of the worst cases, you can tell that in this image, the camera is actually struggling. It fails to detect these ground truth bounding boxes because these are actually fairly severely covered by gravel, not to mention a very bad lighting scenario. And what's particularly curious is there's a fastener here that looks like a fastener, but it's actually not a fastener because it's broken off. The network actually successfully hedges against these detections. So some benefits of Fastnet are you have an active learning potential. So in conventional object detection, if you want to deploy the network onto the field, and if you want it to return back images that it's very unclear about, it's not exactly trivial how you would formulate that problem. But in the case of Fastnet, it's really simple. You just use the entropy of the output map. So this is the Shannon binary entropy equation. You just get the entropy of the output map. If the entropy is high, if the entropy is above a certain threshold, you can then pretty confidently say that the network is not very confident about this image. You hand label the image and then get the network to train on that image to improve the network performance even further. You also have a more informed learning target. You could argue that getting the network to train against semantic segmentation maps is a more natural representation of the ground truth data as opposed to training against a bunch of values that arbitrarily mean boxes. And it's also really easy to engineer loss function. If you've seen any of the loss functions for object detection, you usually know that there's a lot of hyperparameters to tune. You have things like intersection over union parameters to tune. You have class label losses to tune. But in the case of Fastnet, it's really simple. You just compare the output maps. You may argue that the contour finding algorithm is a bit more computationally expensive than the non-maximal suppression algorithm. But this is actually beneficial to us because more of the computation is offloaded to the CPU. The CPU is a serial processor. This may at first look like it's a disadvantage, but you could actually train it as a sync pool operation. Sorry, you could actually run it as a sync pool operation. So what this means is on the left here, you actually see a round robin operation for running conventional object detection tasks. You would take the image, pass it through the neural network, which resides on the GPU, get the outputs, pass it back to the CPU, perform the non-maximal suppression on the CPU, and then repeat. But in our case, you can actually stagger it like that, where the GPU processors and the CPU processors can run almost in an asynchronous fashion. And by doing this, you get more frames per second. In our experiments, we actually found that with about 10 or 50 more frames per second, which already pushes it beyond what is reasonably considered fast. Yeah,
Sorry
some
for
future
the
potential.
interruption, but you still have 2 minutes.
Okay. Some future potential of Fastnet will include more object classes. So how you would do this is just add more feature layers, just add more output layers at the output map. So if you want to predict, let's say, the sleeper of a rail, you could just add another layer at the output that has a saliency map for the rail, for the sleepers itself. Yeah, you do it by more output layers. You can also test different loss functions. There are different loss functions like MSE, BCE, and focal loss. In our experiments, we found that MSE actually performs much better. This could probably have something to do with the output downscaling, where the pixels at the edges of the detection boxes are not very clear. You could also downscale the output for even more speed. So the contour finding algorithm runs in ON time, which is already great. But if you need more speed in a scenario where your CPU is not particularly powerful, you could downscale the output map by using a, let's say, max pooling operation, a 2-by max pooling operation, and then your output map would be 1/4 the original size, and then your contour finding will be much faster. Yeah, that's the end of my presentation. Thank you. Any questions?
Thank you for your presentation. You have 3 minutes for questions. Any questions?
Hello, Junjat. Thank you for the presentation. I really enjoyed it. I didn't really understand why your neural network outputs 200 by 64.
Okay, so what actually happens is it's a fully convolutional network. Let me just go back to that slide. Yeah, so it's a fully convolutional network, correct? Where your input is 1 by 1600 by 512. So in a fully convolutional network, the output is not something like the output doesn't represent an output from, say, a fully connected layer where where your input to the fully connected layer is a fixed size and your output is a fixed size. In a convolutional network, your output would just be a certain function of the input size. Does that make sense?
Okay, so in your case, what does it actually represent, the output?
All right, so the output is actually literally this. I think a more representative example would be, yeah, the output would then be literally a saliency map. And then from this, so this is actually the ground truth, but the output would not be much different from it. This is what the network is intended to output. From this output, we then perform a thresholding, where we crush out values that are below a certain threshold value. And then from then we get like very nice contours, and then we perform a contour finding algorithm on it.
Okay, so your output, I could think of your output as an image of a size 200 times 64.
Yes. Yeah.
And then how do you compare with the ground truth? Do you resize the ground truth, or?
Yeah, we do resize the ground truth, and this is actually a really interesting topic, because you could argue that the ground truth is then a lower resolution than what it should be. And then we've actually found that because of this, training the network with MSE loss and BCE loss actually cause the network to perform 2 to 3% better if trained with MSE loss. We think this is because when you have a downscale segmentation output, when you have a downscale ground truth, the precision at the edges is not particularly accurate anymore. And because of that, the network will tend to produce, like, as you can see, like the edges of this is kind of grayed out. It's not exactly one. And then if you penalize the network and force it to predict a 1 or a 0 for these edges, as in the case of BCE loss, where you penalize it more, the network actually tends to perform worse. So one thing we've tried is, because the output is now a downscaled map, the edges would not necessarily be very clear. So to boost even more performance, you could take the ground truth map and you run a Gaussian blur over it. You treat each output pixel as a Gaussian, and then you just convolve it across the image. And we found that again increases network performance again, but that's not actually done in this paper.
Why don't you force the neural network to output actually the same size as the size of the input? So kind of reverse.
So like you totally deconvolve it to the same size?
Yeah, exactly.
Yeah. That's actually possible. But in our practice, we found that by doing that, the contour finding algorithm would take slightly more time. Yeah. There could be something that's done. It's just not something that we've thought of yet.
Maybe it would be interesting just to see from the point of view of precision and accuracy how the results are impacted. Okay, thank you.
You're welcome. Any more questions?
Okay, so thank you. So our next presenter is Aisha Abdullahi. Just going to share my screen. Presenting dates, fruit classification using convolution neural networks. The floor is yours. You have 10 minutes, and I'll notify you on the 10th that you still have 2 minutes. The floor is yours.
Good evening, everyone. I'm Aisha Abdullahi. I'm here to present date fruit classification using convolutional neural network. So, so a bit of a background for this research. According to the Food and Agriculture Organization, KSA is the world largest producer of date fruit. And by the way, I need to just say I'm from the Prince Sultan bin Abdulaziz University, which is located in Saudi Arabia, Al Kharj city, which is a city that's known for its agricultural background, specifically to produce date fruits. So date fruits are not only the major fruit crops cultivated in KSA, but also considered the most valuable natural resource in many other countries. Date fruit is rich in dietary fiber with global commercial value due to its nutritional and medicinal and medicinal value in curing and preventing various diseases. There's a lag here. So the motivation for our research is specifically to recognize the 3 types of date fruits that's known as Ikhlas, Neptune, Sultan, and Shiashi. The 3 of them are the most popular date fruits in Saudi Arabia. So normally, date fruits pass through 5 maturity levels. The first level is when it's totally immature fruit. It's called Khmeri, Khlal, then Rutab when it's ripe and later brownish, and then pre-Tamar and Tamar when it's totally ripe and a bit raisin-like. So the harvesting of date fruits is performed to its maturity level, according to its maturity level and type. And these 2 factors are critical when deciding when to harvest and not, and also they impact significantly the profit. So the grading and sorting processes of date fruits is still complex task and industry requiring great deal of human expertise, and until now most of these tasks are done by human examiners, which is a bit imposes a lag and some mistakes and other errors. And I need to just clarify what grading means. It's like knowing what stage this date is in, and also to kind of remove other elements from the ground or dust and other things that can enter into the crop. And the sorting process of types and maybe grade. So our research objective here is to investigate the application of deep learning on date fruits images with no prior feature engineering. Here's our main point, or any other feature selection, specifically based on images of the date fruits. Then we analyze and find optimal parameters for deep learning neural networks to differentiate between the 3 types of date fruits, and if we're successful, to propose an efficient framework for date fruit classification using CNN. So our proposed system architecture goes through 5 stages: image acquisition, image pre-processing. I mean, this is an optional stage, and then model building. Just go back to image pre-processing. Mostly CNN is known to remove most of the noise and background and other things, but we wanted also to test whether the model will be faster or not. So we added a bit a level of image pre-processing and model building, and then optimization of the model, and finally the model evaluation. So for the image acquisition, mostly it was done for the dates in their root-up stage when it's fully ripened, and it was done using our normal, very accessible iPhone 7 mobile phones. This is a kind of a experimental process. It's not funded greatly by any company. So the dataset contains 1,055 different images of each date cultivar. So we chose like 3 date cultivars, the Ikhlas and Shiashi and Neptune Sultan. Each one of them had 1,055 pictures. Each of these images contained only one date fruit with a white background, uniform white background, such as in the image on the. And also we did image pre-processing, removed the noise and the background, and as a first step, using adaptive thresholding and Sobel operator to extract the foreground image map and edge information respectively. And then we found the bounding box of the image and cropped the image based on that. Clearly, there is a bit of background left in the image, but it removes a huge deal of the background as well. So we ran our experiments on both versions of date images, the original and the so our model is CNN architecture, contains convolutional layer, pooling layer, fully connected layer. So the convolutional layer applies convolutional kernel on input data to create feature maps on output from previous layers and acts as a feature extractor of the network. And here we kind of the base of our premise or our kind of hope that we will get a good classifier. But then we normally, as the CNN normally contains pooling layer, merges semantically similar features to reduce the feature numbers and invariance across minor modification. And finally, both were linked, the output was linked to fully connected layer. So specifically, our network contained 4 convolutional and pooling layers consecutively after each other, and then followed by 2 fully connected layers. And we optimized the model using five optimizers: ADAMAX, stochastic gradient, and AdaGrade and RMS prop. Just to experiment which one would perform faster than the other. And so we have like a heavy machinery here. I mean, our system is very heavy. The number of parameters is huge. And we wanted, or as you can see, we kind of experimented on 5 optimizers. This was enabled using Google Colab, which kind of given us a environment without prior installation or anything. And we used TPU for our training acceleration. This gave us a really fast time for our training. So for some of the normal experimentation that happened in 2 minutes, maybe, or 3 minutes, were happening in like seconds, less than seconds in the TPU training acceleration. This required us to upload our data set in Google Cloud Storage, which is a bit costly, and I wish I could have presented it now, but I removed it since it is billing me every month. My account has already exhausted the free storage. And so it was extremely fast, and we were able to experiment with all the optimizers and change the parameters quite often. And so this is the first experimentation. And in this image here, we can see the performance or the accuracy of the 5 optimizers. The stochastic gradient descent was a bit slow, but ADAMAX and ADAM and PS prop, I think, was much faster. And here also we can see the loss of the training process. And Also, we kind of tested the time. My experience here as I was doing the experimentation, it was too slow comparing to the next experiment. The first experiment, to clarify a little bit, was done on the full picture with the background included. But we can see that the ADAM classifier has gotten up to 99.22 accuracy, which says a lot about how strong this model is for training the cheaply acquired pictures of the date fruits. And also it was done in considerably short time. And then we tried also to do the same experimentation on the cropped pictures, and we can see almost it's here flopped a little bit, sorry. The accuracy is on the left side, and it achieved pretty much the same results. But my feeling, as I was doing, I mean, I've done many experimentations to do this. This was much faster than the other one, and mostly converging to the almost perfect results in first epoch or second.
I'm sorry to interrupt, but you still have 2 minutes.
Okay. And this is the time. You can see it's much faster, and Adam has recognized the pictures fully, 100% accuracy of the images. And here it's the confusion matrix. On the right, you can see with a background included, and on the left, you can see without background, cropped images. And you can see here each cultivar was recognized fully 100%. And sorry, and behind the model, just to give you a bit of sense of what's going on, this is the feature map that was we acquired from the CNN layers. This is one of the layers, just to show you what was the networks it was dealing with. And this is a visualization of the activation at the end, and you can see that it correctly knows where the picture is. And with other also methods of visualization, we were able to see what type of features was recognizing at each level, comparing to other results. Other related works, most of them use texture, size, water movement, and other methods. We can see here our method almost outperformed most of them. So in conclusion, we can see our system obtained results that testified to the efficiency and generalization ability of the developed CNN architecture to discriminate between all pictures. And the comparative also study with other published work reveals the superiority of the proposed system with improved accuracy. So finally, this system was done by the education system. It's not totally by the industry or something, and we hope by taking the advancement of 5G technology, we can integrate the developed system with widely available smart mobile application to make it possible and affordable for local farmers to reduce the lag and the cost of human labor in sorting and grading the date fruit crops. I reach here the final point of my presentation. Thank you so much.
Thank you for your presentation. You have 3 minutes for any questions. Any questions?
Okay. Any question there?
Hello, Aisha. Thank you very much for your presentation. I have a question concerning how did you split the data between training and testing? I didn't find it very clear from the presentation. So were the results of accuracy presented on the training set or on the testing set?
No, of course, we've split the data into training and testing, and it was like 2/3 for training and 1/3 for testing. And this was done using TensorFlow, or I think sklearn random split of the data. So it wasn't performed on the same training. It was performed on a new set of data unseen before.
Okay. Have you considered using some type of transfer learning? Especially
Yes,
because you don't have a very large data set.
Yes, we've tried. Actually, I mean, in this project, we worked a long time, and I tried it using MobileNet, I think, and other pre-trained models available on TensorFlow, and they all almost achieved the same level. Here we achieved like 100%. They kind of struggled for some time to forget, I think, some of the images available in the trained data. So it almost was comparatively same level. We didn't see superiority for the pre-trained models. It was almost the same.
Okay, thank you.
Cheers. Thank you for asking. Anyone?
Okay, any more questions? Okay, thank you.
Thank you so much, everyone.
And now we will move to our next presenter, Meron Biswas, with a paper titled DRLAS, Digital Record Keeping and Land Administration System Relying on Blockchain. The floor is yours. You have 10 minutes, and I'll notify you on the 10th that you have 2 minutes remaining. Thank you. I'm sorry, the presenter, Madam Biswas, is here.
I think Basil, we can move on to the next presenter.
Okay, so
He's here, but he is not responding our query. I think he is so. No.
So our next presenter is Addison Montes with a paper title of Conversion of Proprietary 3D Printer for Open Source Utilization. The floor is yours.
Okay, thank you. Can you hear me?
Yes.
Okay, I'll share my screen. Okay, so good morning, good afternoon, and good evening to my fellow researchers, session chair, and facilitators. I'll be here to present the conversion of proprietary 3D printer for open source utilization. So this is a project or a research by FabLab Mindanao of the Mindanao State University Legal Institute of Technology in the Philippines. So the authors are yours truly, Edison Montes, Hilas Marias, Ernest Janis Canilla, and Limuel Clark Velasco, who is also here in this conference and is the manager of FabLab Mindanao. So let's discuss first 3D printing. So 3D printers are machines that carry out a form of additive manufacturing which create physical objects from geometrical representations by successively adding materials. So more than just being an additive shaping principle, 3D printing covers any of the various processes in which material is joined or solidified under computer numerical control. So the motivation for this research is to make this obsolete proprietary 3D printer into open source. So why do you want to make it an open source? So let's discuss proprietary. Mostly proprietary software consists of one-stop shop experience whereby the producer or the manufacturer provides almost all the applications and tools you require. However, one of the biggest drawbacks of proprietary software is the licensing fee of the software, and the products can be expensive and not free to source, as is the case of the printer being converted here. So basically, it's printing filaments are much more expensive than what is available for open source utilization. So For open source, the main and primary advantage of open source software is that the cost, which is next to nothing. The term free can be coined with overall cost and more to do with freedom from restrictions. So proprietary software can be costly until you're creating hindrance in organizational growth, which is reduced in the open source movement. So here in this study, we have three stages in our methodology. So first is the assessment of the subject machine or the 3D printer, in which we carefully identify the parts that are needed to be replaced, which components can still be repurposed or can be used for the new machine. And then the second stage, which is the machine conversion procedure, wherein we carefully considered how to convert and what materials to procure for the conversion. And then finally, we have the performance evaluation, which determines whether our machine is satisfactorily performing its basic function as an open source 3D printer. So first, here are the schematics for our study. So figure 1 is the result of phase 1 of our methods, which shows the components in red to be replaced from the proprietary 3D printer in the schematic diagram. So here we've identified the basic and fundamental components of a 3D printer, and then we mark those need to be replaced in red. So figure 2, as a result of phase 1, we have produced this conversion procedure to carry out for the assessment of the machine. So here in this figure 2, at the upper part of the assessment subject machine, that is the phase 1, and then the conversion procedure is the phase 2. So after our results in phase 1, we then repurpose and replace the materials, and then there were initial tests conducted, and that goes in iteration fashion. And then the next, the open source firmware flashing, and then functional tests, also in iteration mode. And after we are satisfied with the results, we proceeded with the calibration and then the performance testing. So the results showed that in the table 1, here are the components replaced and the replacement parts we obtained. So basically, we replaced the controller, the power supply, the stepper motor, the hot end kit, extruder, nozzles, and basically the firmware, which is an open source one, the Marlin software. Here in table 2 are the geometric evaluation of the 3D printer test output. So this shows our performance evaluation for the machine we have converted. So it shows us that there are three test specimens for 2 printers that we tested. So the open source control 3D printer is a standard or market available open source printer. And then here is our machine here, the converted open source 3D printer. As we can see, we have only tested this through visual geometric evaluation. And on the last column, we identified the best performance. So there is no clear winner or clear, there is no real distinction between which printer performs best, since we identified either either printers to be best at some points. So there are minimal ghosting, elephant's foot, and then there are other issues. But let's discuss how these results are considered satisfactory enough for us a 3D printer machine. So here, 3D print specimens of the converted open source 3D printer were found out to be compliant to the outputs of an entry-level 3D printers. It can be observed that in the test samples from the converted open source 3D printer, there were identified minimal ghosting, and that even established open source controlled 3D printer had imperfections similar to the samples. These geometric and structural faults may perhaps be corrected with analysis and techniques at 3D rendering or splicing stage. So next, I will discuss to you some worthwhile discussions or previous literature related to this. So first, in evaluating a 3D printed output of the converted open source 3D printer, conventional tactile and optical methods were found out to be incapable in the detection of inner geometries or complex surface shapes. And then that's by Lopez et al. 2018. In a state, also a study showed that scanning electron microscopy or ECM was even used to perform factography on the various versions of their printed tensile specimens. That's by Torrado and Grobson 2016. While these tests are very good ways to completely characterize the output of 3D printed object, the evaluation conducted in this study to the test specimens were limited to optical and visual evaluations of the outputs. That's from a study by Mahish et al. 2004. Material strength of the 3D print specimens may be improved at the design stage, as suggested by a study showing the testing of PLA specimens printed at different load orientations in an entry-level open source 3D printer. That's by Lecture and Waitashik at 2014. So what I mentioned before that those minimal ghostings or the imperfections found in our test specimens can be improved by carefully conducting maybe another study or to incorporate techniques at the modeling stage or the splicing stage of the 3D models. So in conclusion, this study attempted to convert a proprietary 3D printer for open source utilization by conducting an assessment of the subject machine and followed by establishing a conversion procedure and evaluation of the performance of the printer against a controlled 3D printer. So the main issues found for the proprietary 3D printer is the obsolescence of its default firmware, exclusivity of its microcontroller that limits the use of the machine's proprietary consumables, and the non-functioning other components. This study can be considered as successful in converting a proprietary 3D printer into an open source 3D printer by optimally making use of existing functioning components like its overall body, along with other components such as stepper motors, heat sinks, and heating beds. The performance evaluation of the converted open source 3D printer further validates that the conversion process was successful due to acceptable quality of 3D printed outputs generated by entry-level open source 3D printers, or as compared to an entry-level open source 3D printer, which was used as control for the performance evaluation. So we recommend, the researchers or the authors recommend that performance evaluation of the converted open source 3D printers can be improved by testing for other metrics in mechanical benchmarking like tensile strength and impact toughness over and on top of the implemented geometric benchmarking. So what we made use of this for this study is that we only use visual geometric performance evaluation. The researchers also recommend that for future studies on converting proprietary 3D printer for open source utilization, an emphasis on the individual functionality of the existing components should be conducted for materials and cost saving. So finally, the authors would like to thank ICICT 2021 for giving us the opportunity to present this study and for us to contribute in the RepRap or the open source movement for makers around the globe. And then we'd like to thank our institute, MSUIIT, and then FabLab Mindanao for this very nice study. So that's it. Thank you.
Thank you for your presentation. You have now 3 minutes for any questions. Any questions?
Hello, Edison. Thank you so much for your presentation. How long did it actually take you to convert the 3D printer to open source?
Our actual conversion actually took around less than 6 months, but in reality, one can just achieve it in maybe 1 or 2 months, but in our case, it took up to 6 months since we are students also, and this is not our main thesis or dissertation in that sense.
Mm-hmm. And sorry, because 3D printing is not my field, I didn't completely understand. Did you manage in the end to actually convert, well, replace all the proprietary components?
So what happened in our research is that FabLab Mindanao has bought a 3D printer before that was proprietary, and then through the years, that printer was unsupported already, and therefore we can no longer operate it. So we just replaced some parts, some components that are no longer functional, and then replaced with an open source firmware. So basically, it's like a DIY rehabilitation of a proprietary 3D printer.
Mm. Okay, thank you.
Thank you.
Okay, thank you. Any other questions? Okay, thank you. And now our next presenter is Emmanuel O. Asane, and the paper titled Performance Evaluation of Convex Hull Node-Based Heuristics for Solving the Traveling Salesman Problem. The floor is yours. You have 10 minutes, and I'll notify you on the 10th that you have 2 minutes remaining.
Basil, I think he is not here.
Oh, okay.
I'm not able to see him. So we can move on the next presentation.
We are finished with the presenters because the first presenter wasn't present.
So any of the presenter you can call once again if any of the presenter who have missed.
Yes.
Want to present.
Yes, there are 2 presenters. They didn't present, so.
Can you name them once so that if...
Yeah, S.W. Mason and Emmanuel O. Asani.
I think both of them are not here.
They are not present.
So no worries, we can move towards the end of the session.
Okay. I sincerely thank our authors for their excellent presentation in this session and all our participants for being a part of this international congress. I hope this session was informative and knowledgeable as well. All the presenters would be getting their digital certificates through mail within 2 working days. Further all, the papers have already forwarded to the Springer. The publication will be live within 4 to 6 months. Kindly cooperate with the team of ICICT 2021 as and when intimated. I also thank our session chair, Alina Mero, for chairing this session. A token of appreciation to the chair on behalf of the team, ICICT 2021 and Global Knowledge Research Foundation. Thank you for your valuable presence. And dear all, I kindly request all to turn on their cameras for a quick snapshot for the virtual conference.
Thank you, Alina, for sparing your valuable time. And unfortunately, we are not able to meet this year. But I think hopefully in July 2021, let's hope for the best, that things get better and traveling is allowed.
Mm-hmm. Yes, well, I would also like to thank all the presenters and participants to this conference and you as organizers.
Thank you. Thank you.
Thank you. Thank you.